Hello and welcome. In this session, we're going to talk about, we're going to begin our discussion of data types. Before we start with the data types though, we're going to review quickly some of the objects that are in a database and how those are going to relate to both this course series and what you might see on the 7461 test. Now we're going to dive in. We're going to talk about numeric data types and date-time data types. And those are the ones we'll cover in this session. We'll cover the other data types in the next session. At the end of this session, we're going to have a brief discussion about some different considerations you need to keep in mind when you're working with date-time data types. They'll not only help you to pick the right type of data type when you're working with date-time, but also help you to make sure that you've created your application, your front end, in such a way that what you get back out of the database is what you were expecting and hoping to get. So let's start by talking about some of the database objects. What you see here is a list of objects in both these columns that reside inside of a database. These are scoped to a database. On the left side, I've got the objects that you'll see on the 7461 test. And on the right, objects that you probably won't see. I've indicated these may be covered lightly, and I put that in there as kind of a disclaimer that there may be a question that shows up that deals with these in one way or another, but it's not going to be the main focus of any of the questions that are on the test or on the exam. There's also kind of a dividing line here beyond the test. The items on the left are the items that database developers are typically going to be work with, those who are writing queries and designing objects inside of a database. And the ones on the right are the ones the database administrator is predominantly going to be working with. So that also provides a dividing line here. The ones on the left are the ones that we're going to cover in this video series. The ones on the right are ones that would be covered in another series on database administration. Now for each of these objects you see on the left, most of those will have their own session or they'll be covered in one of the later sessions of the video series. So we'll be covering all of these items as we go through the series. Okay, so let's talk a little bit about database data types. So what is it that you need to know? We're going to go over a long list of data types, a couple dozen different data types that SQL Server has available. What is it you need to know about each one? Well, the most important thing that you need to know is when to pick one of them over the other. When you're given a choice between two data types, how do you know which one's going to work for what you need it to do? If they both work, how do you pick one or the other to decide which one's best for what you need? And that kind of comes to this second bullet point here. When you're given a domain, what are the possibilities? Now, in this sense, the word domain is not what a system administrator or a website administrator is going to think the word domain means. It's not www.something.com. It's not a domain name in that sense. In this context, in the context of a database, the domain is a list of all of the possible values. So you have a column. Let's say you have a column that's birth date. What are the types of values that might go into that column? What are valid? What are not? The entire range of possibilities for the birth date column comprises the domain for that column. Now the domain for a birth date column is obviously going to have dates, and maybe dates within a specific time period. That's going to be a different domain than what you'd have for a field that's last name. Last name is going to have a completely different set of possibilities that might be put into that column or stored in that column. Likewise, a domain for age is going to have a completely different domain. You need to discover the domain for your data, and that will help you to determine what data type is appropriate. Now, when we talk about the best fit, what is the best fit for a domain? Typically we mean the data type that is the most sufficient. It's going to cover the entire domain, be able to store all the possible values, but to do it the most efficiently and in the smallest amount of space. That's one thing as we're going through the data types that we'll talk about is how much storage space each one takes. Now there are some data types that are typically going to be bad choices, and we'll point those out as well. These are going to be data types that either almost universally store the data poorly or are no longer in use. They've been deprecated and they've been replaced by something that does a better job. Okay, so let's get started. We're going to start today with numeric data types. So on this slide I have all of the data types that store numerical values for SQL Server. Now they're listed top to bottom in the order of kind of the size of the domain that they can, for the most part, that they can hold from smallest to largest. So let's go ahead and start. We're going to start with the bit data type. The bit data type has a range of 2 values. It can store a 0 or a 1. Now, technically speaking, a bit can actually store a third value. In fact, all of these data types can store an additional value beyond what you see here, and that's the value null. So a bit can store a 0 or a 1 or a null. Now, a null value, when you store a null in a column or in a variable, what you're indicating is that the value for that variable is unknown. A null doesn't mean 0, it doesn't mean nothing, it means unknown. And when I'm in a class, the way I like to show this is by bringing in a box that's been taped shut. Looks like a little present wrapped in brown paper. When I shake the box, it makes a noise. You can hear that there's something inside. But there's no indication on the wrapping around the box what it's in or where it came from. And what I'll do is I'll ask the people in the class, I'll say, what's in this box? And I'll point to someone, and I'll ask them, hey, tell me, what's in this box? Here, I'll even let you hold it. What's in here? And they'll say, well, I don't know. It's like, okay, well, that's a null. I'll pass it to someone else. Is there a 0 in there? Well, I don't know. There might be. Is there a 10 in there? I don't know. Is there something in there? And they'll answer, yes, there's something in there. We can tell there's something because when we shake it, there's a sound inside. So there's something on the inside. There's something rattling. Well, that's what null means. Null doesn't mean no value. It doesn't mean 0. It means unknown. So I have a little soapbox about null. So a bit data type can hold 3 values, 0, 1, and then null, which means it's either 0 or 1, but we don't know which one it is. So example here, an example value, of course, is 1. Another example would be 0. Now the storage for a bit, how much space it takes up 1 byte. Those of you who know your data types and have used data types either in programming languages or elsewhere before, will say it seems a little odd to store a bit and have it take up a byte of space, because a byte is a lot larger than a bit. A bit is actually a measure of storage as well. The way SQL Server works, when you declare a column in a table as a data type bit, that bit takes up an entire byte of space. However, I've got a little note here that says buy 1, get 7 free. So if you create a bit column in your table, that takes up a byte. If you create a second bit column, SQL Server will store the information about that second column in the same byte that it had for the first one. So essentially, you can get 8 bits in 1 byte, but you pay the cost with the first one. So if you only have 1 bit in the table, it still takes up a full byte, but the next 7 in that same table are all stored for free. Okay, so 0 or 1. Usually this is bit data type is used to store values either on or off. Is this true or is it false? Is it present or is it absent? Something that toggles back and forth between 2 values. All right, the next data type we're going to talk about is a tiny int. A tiny int stores values in the range from 0 to 255. So these are all positive, and these are all whole numbers, no fractions. So it goes from 0 to 1 to 2 to 3. Now, the tiny int takes 1 byte of storage space. So if you have a single bit and a tiny int in a table, they both take up the same amount of space. But the tiny int has a larger range. It can store values all the way up to and including 255. The next value is a small int. Now, a small int can hold negative values. You can see here that it holds from negative 32,768 to positive 32,767. I've highlighted the last digit here to show that it's very close. A small int is very close to holding the same number of negative values as it is positive, but it doesn't quite do it. That has the last digit in the number on the positive side, in this case the 7, is one smaller than the positive digit, or the last digit on the negative side, which in this case is an 8. And I've noted that there's several data types that do that, and the other ones I've only shown the positive side. We'll come back to that. But I wanted to point out that it's very close to the same, but not exactly on the positive and negative side. Now, for those of you who are wondering, holy cow, I have to memorize all of this, my opinion, and again, this is just going to be my opinion, is that you don't need to do that. If you don't plan to take the exam and you're just going through this course to gain better knowledge, then really what you need to recognize and remember from these data types is that they get bigger. from tiny int to small int to int, they get bigger. You'll always have your books online available, or you can go and Google it and look it up and see when you're trying to determine, well, what data type should this be? You can look it up really quick. If you're preparing for the test, you'll need to memorize the approximate ranges. But in my opinion, and again, I'll state this as just my opinion, you don't have to know it exactly. I think it'd be sufficient to know that a small int goes from negative 32,000 to positive 32,000-ish. And that maybe if you remember that they're off by 1 on the negative and positive score, then that would be good to know as well. But I doubt you'll be tested on the exact level. For example, I doubt on the test they would say, you have a domain that covers from some negative number to 32,768. Which data type should you use? I don't think they're going to test you on the exact number, but I will think they'll test you on the scale. They may say, oh, you've got a number that goes up to 10,000, or a number that goes up to 100 billion. And then you would need to know, oh, I know exactly where those ranges kind of fall. So I think you need to know the approximate place, but I don't think you need to know it precisely. Now, small int, of course, since it stores much larger domain than the tiny int, it's going to take up more space. And of course, you can see over here that it's doubled. A small int takes up 2 bytes. When we get to a regular int, that doubles again. We're up to 4 bytes now. And an int will hold from plus or minus roughly 2 billion. Now again here, I've shown the positive end, the last digit here being a 7. The negative side will be negative 2,147,483,648 would be the largest negative value that it would hold. And now we get to big int. This is our largest whole digit integer data type. And a big int can hold positive and negative values, starting with a 9 and then 18 digits after that. Here's a good example. If you actually pull up books online, you'll see that maximum number is completely spelled out, all 18 digits, the largest value that it'll show. I didn't include it here in the slide because I didn't feel, again in my opinion, that it's important to know exactly what that digit is. Just to know that, oh, it's a big number, it has 19 digits, a 9 followed by 18 other digits. And to know that, that it's bigger than the int, which only has 2 billion, it goes up to a much larger scale. Now, as I mentioned, all of these here, the bit, the tiny int, the small int, the int, and the big int, these are all whole number or integer numerics, meaning that they don't have any fractional values, no decimal places, and no fractions. They store whole values. And that's going to be the dividing line between these first 5 data types and the ones that follow. The ones that follow all have fractional values that they can store as well. Each one increases in size, so you pay a cost for the larger domain. Now, an int is a very popular data type. The int data type is commonly used for your primary keys. And I want to talk just for a second about the cost of using an int as a primary key. Typically, when you create your primary key, it's very common to start the primary key at 1, so that the first row of the table has the value of 1 in that integer column. The next one has a value of 2, and they increase up as they go. If you do that, you have limited the amount of numbers that you can store by half. So you start at 0 and go up to 2 billion, you haven't used any of the negative portion of the integer value. So you're really storing, you're really incurring the cost, there we go, that's the word I was looking for. You're incurring the cost of 4 bytes, but only taking advantage of half of what it has to offer. If you don't need that many, you'd be much better off choosing a smaller data type with a smaller size. What usually happens is people look at the int and say, you know what, it allows me 2 billion rows, but I actually might need more than that. So I'm going to go ahead and go with a big int, just in case. That's a fine way to do it. Pick a big int up front so that you have, in this case, almost limitless number of rows that you can put in your table. But you pay an extra cost with that. And the cost is doubling the amount of space that it takes to store your data. Instead of 4 bytes to store your primary key, it's going to take 8 bytes. Now, later in another session, we're going to talk about indexing and performance and foreign keys and primary keys. But what I want to point out right here is that if you change your primary key to be a big int, you're impacting several other areas in your database as well. Anywhere where you have a foreign key reference, that foreign key reference is now going to be 8 bytes instead of 4 bytes as well. Anywhere you create an index, if your primary key is your clustered index, any of your non-clustered indexes will have more space taking up in their leaf nodes as well, because they're going to be referencing back to a big int, which is 8 bytes instead of 4 bytes. So you need to very carefully determine what you're going to use as your primary key. And if you use a data type that's either too big or too small, you'll run into some issues later. That's something we'll talk about when we talk about primary keys. So don't worry about that right now. If you've never heard of primary keys, you've never heard of foreign keys, and you've never heard of indexes, we will cover all that. But I wanted to put a little seed in your mind now that making the choice of either too big or too small will dramatically impact what you're able to do later and the cost that you pay later as well. Let's talk about numeric. Numeric and decimal are synonyms for each other. If you declare a data type numeric or declare it decimal, it really ends up being exactly the same thing in SQL Server. And this is our first data type that has parameters. You can see that we have numeric, and then we have an open parenthesis, p, comma, s, and then close parenthesis. This indicates that when you're creating a numeric data type, you provide two additional pieces of information. In this case, the p stands for precision, and the s stands for scale. The number that you provide for the precision tells SQL Server how many digits you're going to you want to have in your domain. Now here I've specified that precision can be between numbers between 1 and 38, meaning that if you do a numeric 38, that will be able to store 38 numbers, so a number 38 digits long. And that's the largest that we can do. And you can specify exactly how many digits you want your number to be able to hold. The scale, the s value, determines where the decimal place goes in the number. Specifically, so the example that I have here, this number here has 9 digits, and the decimal place, there's 4 to the right of the decimal place. This is an example of a numeric 9, 4. It contains 9 digits, 4 of them to the right of the decimal place. So the precision tells it how many numbers can be stored, and the scale really just tells it, well, when you got that long string of numbers, where do you put the period? The precision also determines the size of the data type. So if you have a number between 1 and 9, it takes 5 bytes to store it. So in this case, this number here is our example. If we declared it as a numeric 9, 4, it would take 5 bytes to store. If we stored a smaller number, let's say we only stored these last digits starting here with the 3, and going over we didn't have the 1, 2, it was 345.6789. If we store that inside of a numeric 9, 4, it would still take up 5 bytes. But we could declare a data type of 7, 4 and still hold it. Now, since the precision of 7 falls in the level of 1 to 9, it would still take 5 bytes. So we wouldn't really save any space by declaring a 7, 4, but we would restrict it from not being able to allow numbers that are bigger. All right, so numbers between 10 and 19 digits take 9 bytes, 20 to 28 digits take 13 bytes, 29 to 38 digits, which that's our maximum, takes 17 bytes. So 38 digits, that's a pretty big number. And then the scale that you put with it would say, out of those 38 digits, how many digits are to the right of the decimal place? And that's something that's static. When you declare a column, my column is 9, 4. All of the rows will be 9, 4. If you only give it a value that is 3, 2, it will add zeros on the end, and it will still take 5 bytes to store it. It just allows you, this is the most precise and the largest number that I can store in it. And one thing I want to point out again, just to make sure that it was clear, is if I declare a data type that's between this range, the example that I gave was, I'm going to declare a numeric 7, 4. The 7 falls in between 1 and 9, so it still takes up 5 bytes. In that case, I want to ask you the question and give you a chance to think about it. Why would I ever declare a numeric or a decimal where the precision wasn't the maximum in this range, a 9, 19, 28, or 38? Why would I ever declare a numeric 15, comma, something? Why would I ever pick a number in between here? Well, the answer would be, the only reason that I can think of why somebody would declare a 15 would be if they wanted to make sure that they never stored a number that was 17 digits long, or 18, or 19. They always wanted to make sure that it was a maximum of 15. There's no storage gain by declaring a 15, comma, whatever you want your scale to be, because it's still going to be 9 bytes. So if you don't care about restricting it to have a maximum of 15 digits, you might as well go up to the maximum, which is 19. And that's what I usually see people do, is they'll pick the number along one of the edges here, 9, 19, 28, or 38. I haven't ever run into an application where someone has picked one in the middle where they understood the range. It is possible, though, that you may have one who say, you know what, I want to be able to let them go up to 1 million, but not beyond that. So even though I'm not taking full advantage of the space that I'm using, I'm limiting the values that can be put in. So I'm going to use that to restrict my data. All right, the next data type that we're going to talk about is the money data type. So you can see there's 2 data types SQL Server has for monetary or financial values, money and small money. And as you can imagine, the difference between them is the space that they take, 4 bytes for small money and 8 bytes for money, and also the domain that they cover, plus or minus 200,000 for small money, and 922 billion for money. Now you notice here in the examples that I have currency symbols. This first one here is for the yen, and the second one here, as I remember, is for the pound, if I remember right, when I rolled up this slide. Now, you can pass that in. You can actually pass the currency symbol into the money data type, and SQL Server will accept it. But SQL Server will not record it or remember it. It ignores it, in fact, is what it does. When you get the information back out, SQL Server returns the value without any currency symbol. So if you were hoping that the money and small money in SQL Server would convert your financial data from yen into pounds, from pounds into American dollars, from dollars into rubles, that won't happen. Nor will SQL Server remember what the currency was and tell you what it was when it comes back out. So what you'll get back out for this small money that I have here is 345.1599. What you get back out for this second example is, I'm missing a comma right here. 1,245,643.999. It won't tell you whether that's yen, pounds, or dollars. It'll just give you the value back out. That means that if you're working with international currency, it becomes very important to do whatever conversions you want ahead of time, or to also store another field information that'll tell you what the currency and value is of the item that you're storing here. Now, one thing you may notice here that's going to be interesting is that for 4 bytes, you can store a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digit number. Interestingly enough, here, for 1 to 9 digits on a numeric, it takes 5 bytes. Let's see if I can highlight this here. So 4 bytes for 9 digits, or 5 bytes for 9 digits, 4 bytes for 10. Why is there the difference between these two? Well, one thing you'll notice here is that you're not being able to specify the number of decimal places. Small money is always going to be 4 decimal places, and money is always going to be 4 decimal places as well. With the numeric and decimal, you get to specify how many decimal places you want. In addition, even though we have 10 digits here, we do not have the full range of 10 digits. The very first digit that we can store here is a 2. We cannot put a 3, a 4, a 5, or a 9 into this first digit place. Now, I guess I have to be clear here. You can store a 3. In fact, over here I have an example of a 3, right? But I can't store a 9 in the 100,000ths place here. I can't have 900 and something thousand in my money. The maximum that I have is 214,000. So we're not getting the full range of digits either. But we are storing, in some sense, a greater full range in a smaller storage space. We're getting 10 digits, 9 full digits and part of this 10th in a 4 byte space. That means that if you have an application that really only needs 9 digits, you might be better off, oh, and it has exactly 4 decimal places, you might be better off using the small money. Now, in reality, I don't recommend that you take advantage of that optimization. If you have a column where you're storing something that's not financial, but you've called the data type small money, it's more likely to be confusing to the other developers, administrators that are using the data than it will be to actually be saving the single byte. In that case, I think you're better off specifying your numeric and getting the data that you want rather than saving a byte and using small money. All right, the last data type that we're going to talk about are float and real. I'm going to draw a line here as well. All of the data types above the line are actual precise values. When you put in a value, in this case, let's take the numeric example we have here, 123,000 or 12,345.6789. When you give SQL Server that value, it stores that exact value, and every time you ask for it back, it's going to give you that exact value back out. It's going to be precise, it's going to be accurate. The ones above this line here are also whole digits. They don't have any fractional values. So we have whole digits, fractional values, and above all this are the ones that are precise. The reason I bring that out is that float and reals are not precise. They store approximate values. What that means is that they have a range from small to large, and it's a really, really big range. The biggest number that you can store in a float is a 2 with 308 zeros after it. 1.79 with 308 zeros after it. I was looking at the wrong line. That's a really, really big number. That's a number with 308 digits in it. And you're storing that in 8 bytes. So you're storing that in a smaller place than you're storing a 19-digit number for a numeric. Well, the reason that it's able to do that is it's storing only approximate values. Not every number in that range can be precisely stored. But what SQL Server can do is store the most significant digits. And as I've done the research, there's a formula behind there. And what it roughly comes out to be is you got 2 choices, a 4-byte and an 8-byte choice. The 4-byte stores 7 digits, and the 8-byte stores 15 digits. What that means is it's going to store the 17 most significant digits, the 17 digits that are furthest to the left, the ones that are going to make the most difference. So if you have a really big number that has 100 digits in it, SQL Server is going to store the first 7 or so, and then it's going to store how many zeros come after that 7. So it'll give you the appropriate scale at a number that's close to exactly what you put in, but may not be exactly perfect. Now there's a lot of math involved that, I'll be honest, when I went through and did the research on how does SQL Server store a float, how does it store a real, I didn't understand it exactly. So this is kind of a generalization. So what is it that you need to know? Well, a float and a real will store very, very big numbers and very, very, very small numbers, and then very, very, very big negative numbers as well. But it doesn't store them exactly, and we'll get into a demo where we show you how it's imprecise. But it'll store those values. I did a bit of research, and let's see. I looked up the number. This 1.79 corresponds to 100 uncentillion. That's the technical term for that large number with 308 zeros after it. That's roughly the same size as the number of possible combinations of a 7x7 Rubik's Cube. There's actually smaller than this. You could actually store every possible combination on a 7x7 Rubik's Cube. If you take all the Scrabble pieces in the game of Scrabble and arrange them in different ways on a Scrabble board, the number of possible arrangements of all of those Scrabble tiles on a Scrabble board is actually less than this number. And if you want to get really complex, there's a 1 with 81 zeros after it. This one will store 308, but a 1 with 81 zeros after it, which is a much smaller number than what a float can hold, is the estimated number of fundamental particles in the observable universe. So if you're talking about the quarks and so on that are really smaller than an atom, the number of those particles in the observable universe is a 1 with 81 zeros after it. And here we have a number with 308 zeros after it. The example that I have here is one Google, and I think Google's just a fun number because it's a 1 with exactly 100 zeros after it. And that's definitely way within the realm of what a float or a real can do. Now over here on the side, you can see it's got a range. And this may look similar to the range for numeric and decimal we talked about before. This one, and it really is. Any number that you pass in for a float, the parameter here, the n, any n between 1 and 24 is going to take 4 bytes of storage space. Any number between 25 and 15 will take 8 bytes of storage space. The difference between the ranges here and the ranges that we had for numeric and decimal are that if you pass in a number that's between 1 and 24, it actually functions equivalent to 24. There is no difference. Where with numeric, if you passed in a number between 1 and 9, for example 7, it would limit it to 7 digits. It just wouldn't give you any storage benefit past the 5 bytes. With a float, if you pass in a number in between the range, it actually works exactly the same as if you had passed in a 24. Likewise, if you pass in a 40, it functions exactly the same way as if you had a 53. It doesn't change your domain at all, nor does it change the storage space. So here, there's really no reason not to do 24 and 53. A real, you may notice, doesn't have the parameter. Float has a parameter that you pass after the data type. A real does not. A real is the same as a float 24. So if you use those two data types, they're interchangeable, and they mean exactly the same thing. Okay, let's go ahead and take a look at a demo now. All right, in this demo, what we're going to look at is how to declare a data type, and also how to use it and to see the storage space that's taking. So this first line here is us declaring a data type. So I'm going to declare a variable. I give it a name, and my name is going to start with the @ sign here. That's what tells it that I'm declaring a variable. So the word declare, the @ character followed by a name for my variable, and I'm going to call it my bit variable, and then a type. So I'm going to declare a data type that's a bit. Now I'm going to actually use just this part here without what I had before, just the equal sign. I'm going to highlight this section, and then I'm going to click execute. And then what that'll do is it'll execute only the part that I have highlighted. It'll just execute declare my bit variable bit. When I execute it, it says command completed successfully. So I declared a variable. I didn't give it a value, nor did I ask it for the value back, so it didn't really do much that I could see, but it created that variable with a bit data type. Now what I had in the original was bit equals 0. That assigns a value to it. If I execute that, that runs successfully as well. I assigned a value, but I didn't get the value back out. The way I get the value back out is by doing a select. Select my bit variable as, and I'm going to give it a name, and that gives it a column name, and what I'll see is my bit variable has a value of 0. This as part here is what gave me the name, otherwise it would have just given me the 0. Let's show you that as well. I'll say no column name. It doesn't have a name, this column doesn't have a name, the value is 0. So I used the as to name the column so I'd get that back in my header. Like this. So we use the declare, we give it a name, a data type, and a value. And to see it, we do a select, and then the name again, and then we give it as, and then a column name that we want to see as far as our header. Now another way that we could have done this, we could have done it in 2 steps. We can use select, and then the name of the variable, an equal sign, and then the value to assign the value to the variable. Let's take a look at that. See, it works just the same. I could also use a command called set. This does the same thing again. It sets the value. So it works just exactly the same as it did before. All right, I'm going to do undo and go back to the way it was. All right, now in my select, you have a comma, which indicates I'm going to do a new column. And here I've executed a function. The function is called data length. In one of our future sessions, we're going to talk about all of the functions that SQL Server has available. The data length function returns the amount of space used by a variable or by a column. So in this case, I'm going to do data length, and I'm going to pass it the variable name, my bit variable, and then I'm going to give it the header that I want for that column is called storage space for my bit variable. So now I run all of this, I will get 2 columns and 1 row. 1 column for the value of my bit variable and 1 column for the storage space for my bit variable. So as you see here, the storage is 1, and this is measured in bytes. So my bit variable took up 1 byte. As you remember, for the bit, the first bit consumes a byte, and the next 7, when you're storing it in a table, consumes the rest of that byte, or you get them for free. Buy 1, get 7 free. So here you can see that our bit is actually taking up a full byte of space. All right, let's move on. I've skipped the tiny int and small int, and I moved right on to an int. I'm storing the value 500. And again, I've changed the name, my int variable instead of my bit variable. I have the same basic select statement where I'm getting the value out and determining or viewing how much space it took to store that. So here's the value. You can see that it got assigned successfully, and when I asked for it back, it gave me the right value back, 500. And as you remember from the slide, an int takes up 4 bytes of space, and that is exactly what it's taking up, 4 bytes of space. So I confirm that that's correct. Yay! All right, here we have a numeric. This numeric, we're declaring it is 19, 4. Do you remember what that means? That means we can store up to 19 digits, and 4 of them are to the right of the decimal place. So here I have a value, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3. So this number has 13 digits, and 4 of them to the right of the decimal place. So if I run this, I get the value back out, and it took 9 bytes. Remember, the next step down is a 9, 4. So if I change this to a 9, change my number so that it has less than 9 digits. Now we have 7 digits. You can see the storage space that's taken up is just 5. All right, let's move on to a money data type. Here we're to declare the money. We're using $52.13 is what we're going to pass into our money. You can see when we get the value back out that the currency sign, although it didn't throw an error to put the currency sign on, nor it didn't save it either. So it's valid, it's okay to pass in a currency sign, but SQL Server won't remember it nor do anything with it, it'll just ignore it. And again, as we got the money is 8 bytes, storage space, a small money would have been 4. All right, our float 53, so this is our imprecise data type. But it stores really, really big numbers, as in scale of the universe, and really, really, really small numbers, as in microscopic distance between atoms type of numbers, and smaller than that actually as well. The number that we're going to pass into it is a 10 with 100 zeros after it. So this is 10 Google that we're going to pass in. 1 with 101 zeros after it, right? Because we got 100 zeros, and then the 10 had a 0 with it as well. And you can see that what we get back out is 1. And the E means times 10 to the 101th power. So this is a 1 with 101 zeros after it, which is exactly what we passed in. We passed in 10 with 100 zeros, which is the same as a 1 with 101 zeros after it. As you can see, we got that for 8 bytes of space. So it did that, and it stored it really efficiently for us. Again, it's just storing an approximation. It's not storing the exact value. Let's look at an example that really brings that out. What I'm going to do here is I'm going to declare a variable that's a real, which means that it's a float, float 24. And the value that we're going to put into it is 0.01, 1/100th. And when we do that and we look at the value, we can see that sure enough, it stored 0.01, which is what we asked. But what happens when we add up that variable 10 times? So we're going to take 0.01 plus 0.01 plus 0.01 plus 0.01. We do that 10 times. Well, what is the result that we should get back out? Well, 0.01 10 times added is 0.1, or 1/10. But with the float, it can't really store 1/100th precisely. 1 over 100 is one of the numbers that it can't store exactly. It can only store an approximation of it. So when we add it up 10 times, a little bit of error is introduced each time. And what we actually get back is something very close, but not exactly 1/10. It's just a little bit smaller. It's 9.9 tenths. It's 0.099999, almost 0.1, but not quite. This is something that you'll need to be careful of when you're using floats and reals. Because they're approximations, some of the values that you give to it, it may not store exactly precise. And this becomes really important when you are storing values that you then do math against, either adding, subtracting, multiplying, or dividing. Because those very small errors can become magnified when you're doing math. You'll notice this especially when if you use a float or a real for financial applications. You're computing taxes and bonuses and percentages and discounts. That every once in a while, when you're doing your calculation, you'll end up with a value that you didn't expect, and that's because of these small storage and precision errors that show up with float and real. They can store really big numbers, and they can store really, really small numbers, but they don't store them precisely. So you have to be ready for and expect some of these small math errors to occur. All right, let's go back now and let's talk about date and time data types. Okay, we're going to talk about 6 different date-time data types. The first 2 are ones that have been around forever and in SQL Server, and the last 4 are ones that have been more recently introduced. The first 2 we're talking about are date time and small date time. And as of the other data types, the word small means that it has a smaller domain, but also a smaller footprint. Takes up less space to store. Small date time takes up 4 bytes. Date time takes up 8 bytes. Small date time allows you to store dates between January 1st, 1900 and June 6th, 2079. And it has minute precision, meaning it doesn't store seconds. It stores the hour and the minute inside that range. So an example of that would be August 9th, 2012, 1:32 p.m. No seconds, but falls within the range of 1900 to 2079. It'll store that information in just 4 bytes. Datetime has a much larger range. It goes from January 1st, 1753 to December 31st, 9999. And the time component has 2 1/3 digit precision. And it takes 8 bytes to store it. Now, what do I mean by 2 1/3 digit precision? What I mean is the last digit, the third digit in the seconds, fractional seconds, has to be either a 0, a 3, or a 7. So the example I have here is pretty close to the one above, a little bit different time on the minutes. 11423.883, so 883 fractional seconds, 883 thousandths of a second. This last digit, in this case the 3, has to be either a 0, a 3, or a 7. If you pass in something else, like a 9, or a 2, or a 6, SQL Server will round it to the closest digit. Now this is really kind of interesting, I think. One is the fact that they've limited the scope of this last digit, and the other one is that they picked the year 1753. Now I haven't contacted Microsoft to find out why, but I did a little bit of research because it seemed really odd. And I asked myself, what happened in 1753? And I actually found an event in 1752, in 1753, that made some sense why Microsoft might have picked this date. And that deals with the Gregorian calendar. So here's how it works. In 1582, the Pope and the Holy Roman Empire moved to the Gregorian calendar. They had found that over time, because of changes, because the Earth doesn't rotate the sun in a perfect number of days, their calendar dates had gotten off. And for them, they were really concerned about Easter being on the right day. And so they decided to move to a Gregorian calendar, which handles leap years the way that many of you might be familiar with, where every 4 years, February has 29 days, and except for years that are evenly divisible by 100, unless they're also divisible by 1,000. And before that, they didn't have that in place, and so over time, the calendar had kind of shifted a little bit in the solar cycle. So in 1582, they decided to go to what they call the Gregorian calendar, and they took a hit on their days, and they said, oh, we're going to skip this many days and that's how we're going to work it. Well, the Holy Roman Empire converted to the Gregorian calendar then, but the rest of the world didn't. In fact, for some of them, it took over 300 years to decide to adopt the Gregorian calendar. I believe, if my research is correct, that Greece adopted the Gregorian calendar in 1923. Denmark adopted it in the year 1700, and for Denmark, they went from February 18th, the next day after February 18th was March 1st, so they skipped all the rest of the days of February, went straight to March. So the trouble that you have with dates back in history is not only do you need to know the date, but you also need to know where it happened. It's not sufficient to say, oh, this event happened February 19th, 1700. You need to know, well, did it happen on that day in Denmark, which actually that date doesn't exist in Denmark, or did it happen in Greece, or did it happen in Italy, or did it happen in Britain? You need to know more than just the date. You need to know the location in order to know what day that was in other places in the world. Now, Sweden, Finland, Scotland, and Great Britain adopted and moved to the Gregorian calendar in 1752, 1753-ish. So my guess is that is why SQL Server and Microsoft, not why SQL Server decided, that's why Microsoft decided that the minimum date time value would be 1753. I think they took kind of a British and perspective on it and said, dates prior to that, we're not sure how they're going to coordinate and correlate, therefore we're just not going to allow those dates. So that you can't say, oh, I did a date diff between this year in the 1500s and this year in the 1900s, and it was the wrong number of days because of the Gregorian calendar change, blah, 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 blah. I think they just decided now we're just going to start at 1753. That's when the Gregorian calendar was adopted in Britain. Therefore, that is the earliest date in the Gregorian calendar. Now, as far as the final digit, that third digit only being 1/3, my guess is that my guess is that they took the range here from 1753 to the year 9999 and said, okay, if we want to store this many years, how much time can we store? And I said, well, we can get 2 digits completely, and we'll lose a little bit, that we could get a bit more than that, or a bit, that's kind of funny, a byte more than that. We can get a little more precision than that, but we can't get a full digit's worth of precision, and so they took what they could. It makes it really kind of odd, but it did give us the most precision that they could possibly give us. There's at least a little bit more information, although it kind of gives you the thought that, oh, I've got 3 digits, when you really don't. You've really got 2 1/3 digits. All right, so there's my philosophy on why the date time range is a little bit messed up. But regardless to say, you probably don't need to know the dates of when Greece and Denmark moved to Gregorian calendar, but an idea that the date time only goes back to the 1700s. It goes all the way forward to the year 9999, where we'll have a Y10K issue party. I'm sure we'll all be reprogramming everything to handle 5 digits in the year. All right, date time. So small date time and date time. Now, in 2008, there are some new data types that were introduced, and those are the date time 2, and date time offset. Date and time are fairly simple. It's just a date time broken into pieces. Here they've taken and said, okay, we're not going to worry about the 1753. We're going to allow all the way back to the year 1 and all the way forward to 9999. So they removed the restriction 1753. And if you're only storing a date, you can do that in 3 bytes. Well, that's awesome, because you get a much larger range to give to the date time and a much smaller space. Of course, you don't get any time. You only get the date. But there's a lot of applications where all you need is the date. You don't need the time. Maybe you're tracking a birth date, for example, and you don't care the time of birth. You only care the day that they were born, which is usually the case. And so unless you're working for a hospital, I guess I should clarify, hospitals would care about the time. But most of our other applications just care what's your birthday and how old are you, not what time were you born. And I think many people would be hard pressed to really come up with that information. I know that I would. Although I must admit that I do know the time my children were born, but now I'm getting off topic. Okay, so date in 3 bytes, and our time now takes a parameter. And the parameter that it takes is the number of decimal places or fractional seconds that you want for precision. The default is 7. Yes, from 3 digits to 7 full digits of second precision. So for your applications now that need really precise time values, you can do that, up to 7 decimal places of seconds. And it can store any time value from midnight to midnight with that precision. Now the n, as you can imagine, you get to specify the n, and so you also then thus get to specify the storage space. And it's either 3, 4, or 5 bytes. And it depends on the range that you gave it for the number of decimal places. Now the range here is going to be similar to the range that you saw for numeric and decimal, and that if you specify something in between the range, it limits the domain, but doesn't free up any additional storage space. So if you have no decimal places, 1 decimal place, or 2 decimal places, they all take 3 bytes. 3 or 4 decimal places take 4 bytes, and 5 to 7 decimal places take 5 bytes. Now I'm going to come back and show you something interesting, because I think I know the question that you just had in your head, but I want to take one step further, and then I'm going to come back and answer it. SQL Server also has a new data type called a datetime2. A datetime2 is like datetime. It has both a date and a time component. It takes up the parameter here for the fractional number of seconds. Datetime2 has the same date range that date has from the year 1 to the year 9999. It has the same range as the time, the number of decimals to n. So it really is, datetime2 really is essentially a squished togetherness or a combination of a date and time data type together. In fact, if you look, if you have your time, the n here on datetime2, I should clarify again, is the number of fractional seconds on the time, just as it was here for the time. And in fact, if you look, if you have 0 or 2 fractional seconds, 0, 1, or 2 fractional seconds, your datetime2 takes 6 bytes, which is exactly the 3 bytes for the date plus the 3 bytes for the time. Similarly, if you pick 3 to 4 decimal places for your datetime2, the time on your datetime2, your storage space is 7 bytes, which is exactly the 4 bytes for the time and the 3 bytes for the date time. And, drum roll here, if you pick 5 to 7 decimal places for your datetime2, it takes 8 bytes, which is exactly 5 bytes for the time and 3 bytes for the date. So really, the datetime2 is really just a combination of the date and time data type together. So, this is where it gets interesting. Let's compare a datetime2 with the old SQL Server 2005 datetime data type. Well, with the datetime, we got 2 1/3 decimals on our time for 8 bytes. Well, what do we get for 8 bytes in SQL Server 2008 and 2012? Well, for 8 bytes, we get 5 to 7 decimal places for the same storage space. But not only do we get 5 to 7, it's not the last digit is some fractional, it is full range. 0 to 9 in every decimal place, all 7 decimal places. And again, for your 8 bytes, for no additional charge, call today. If you call within the next 5 minutes, we get a larger range. Because in 2005, with our date time, we stopped at 1753. Now, with our datetime2, we go all the way from the year 1 to the year 9999. So for the exact same storage space, 8 bytes, we get 1,700 additional years, and we get, let's see, we had 2 1/3, subtract that from 7, it's 5, we get 4 2/3 more decimal places for the very same amount of space. Wow, now that is nice. That is really good. Why would we not use a datetime2 instead of a datetime? I can think of one reason. I'll come to that in a minute. Let me show you one other thing here. This is interesting. Let's say we said, you know what? I don't need 7 digits of precision. I've got this application and I'm storing the appointment time or an order date time. And I really don't care to have it that precise. The 2 1/3 digits that I had, that was sufficient. So I'm good just going with 3 digits. Datetime2, 3. Okay, Well, that's great. Well, we can do a datetime2, 3, with 3 decimal places, and we save a byte of storage space. Well, what if you didn't need any decimal places? I'm storing an appointment time. You're supposed to come in at 9 o'clock. You're supposed to come in at 9:30. I really don't care about the fractional seconds. Well, okay, a datetime2 0 is 6 bytes. That's 2 bytes less than the datetime that we had before. Yes, now we've given up some decimal places, but if they're decimal places that we didn't need anyway, we can save space. So in every case, datetime2 is better for less storage space than the datetime. So why would you not convert all of your datetime data types over to datetime2? The only reason that I can think of that you wouldn't do that is if you need to be backward compatible with SQL Server 2005. If your application is still supported on 2000 or 2005, the datetime2 isn't an option. It's not there. It was introduced in 2008. So you don't have the choice of making a datetime2. And in that case, you still need to keep using datetime until you can move off those platforms. You no longer have to support that platform. Then you can convert everything to a datetime2. Other than that, it seems like datetime2 is superior, and in most cases, it's going to be smaller than what you had with datetime already. So it's a good move. All right, let's talk about this last data type. The last data type that we're going to talk about is a datetime offset. Now, a datetime offset really is just a datetime2 with an offset from GMT added onto it. So the n that we have here, the parameter that we're passing in as an n, is the same as it was for datetime2, is the same as it was for n, or for time. It is the number of decimal places of fractional seconds that you want. And the example here you can actually see, here's a date, 4/13/4457, wow, that's way off in the future. And here's the time, 4:52 p.m., 17 point, and then there's all these fractional seconds. And here's the piece here at the end that's new, and that is the date time offset from GMT, negative 6 hours from GMT. So this has a component in it that gives you not exactly a location. We'll talk about that in just a minute. It doesn't quite give you location, but it does give you an offset from GMT where it's associated with that date and time. Now this, of course, this doesn't come for free. The offset costs 2 bytes. So as you look at the difference between the storage space for datetime2 and the storage space for each of the levels of precision for a datetime offset, you can see that each one is 2 bytes higher. That's fairly easy to remember. It takes an additional 2 bytes off of what the datetime2 is for a datetime offset. Okay, let's take a look at some examples. Okay, we're going to look at 3 examples. First one here is a small date time. And we're going to pass in June 12th, 2013, 3:21:55. So that'd be 3:21 p.m., 15:21:55 is our time. We're going to use the same structure that we had in our previous demo, where we declare the data type and pass a value in, and then we get the value back out, and then we look at the amount of storage space that it took. So let's look here at our small date, and here's the value that it gave back out, and it stored it in 4 bytes. What I want you to notice here is what it did to the value. You'll notice that the seconds that we passed in were 55 seconds. But small date time doesn't store seconds. So what SQL Server did was it rounded the value to 22 minutes. So in here you can see the precision level that the small date time had, that it wasn't carried through. It had to round it for us. Okay. If we take here, our second one is a date time data type. And here we're going to pass in the same day, almost the same time. We're going to pass in some fractional seconds, 0.002 seconds in this case. When we run this, see, here's our value. It took 8 bytes to store it. And again, what I want to point out here is that what it did to our fractional seconds. If you remember right, the date time, this final digit here has to be this last digit, which, that didn't quite highlight that last digit. All right, there we go, the 2. This last digit has to be either a 0, a 3, or a 7. In this case, we gave it a 2, and so it rounded it to a 3. We did get some fractional seconds. We got the seconds where we lost the seconds in our small date time. So we have seconds, but we weren't able to keep the last level precision. It had to round it to either a 0, a 3, or a 7. Let's take a look and see what happens when we change the year. Remember that a date time goes to 1753, and my guess is because that's when Britain adopted the Gregorian calendar. So Microsoft assumed there were no dates before that in the Gregorian calendar because that's when it began. And we put a date back further there. It says the conversion of a varchar data type to a date time resulted in an out of range value. So it gave us an error. However, if we had used a date time 2 instead, we certainly could have put in the year 1013. Here we go. That one took it just fine, the year 1013, because a date time 2 can go back all the way back to the year 1. And as you look at this, you can see that we've got 4 digits of precision, kept all 4 for us. So, and this one only took 7 bytes. Our date time took 8. So here we have 4 digits of precision and 7 bytes, and we got the year that we're looking for before. So when you're looking at date and time data, you really need to look again at your domain. What are the possible year values? What are the possible time values? Am I only looking for time? Am I only looking for date? Do I need both of them together? How large of a range do I need? And do I need to keep track of fractional seconds? And do I need to keep track of an offset from GMT? Answering those questions will help you to decide which data type fills your domain, can cover your domain, actually, I guess, not fill, but cover your domain, and do so in the least amount of storage space. All right, let's go back to our slides. The next thing I want to talk about is some issues that you need to remember when you're building your application around date and time values. And these are things that are not necessarily going to be specific to SQL Server, things that you need to consider when you're building an application around date and time values. And also when you're making sure that as you store values, you're storing them in a way that you want to get them back out. So here on this slide, I have 2 date time values. They're on the same day. One's at 1:15 a.m. and one's at 1:30 a.m. And the question that I have for you that I want you to answer, and I'm going to pause for just a minute so you can think about it before I give you the answer, is which of these 2 events occurred first? You may think that that's a very simple question. Well, 1:15 comes before 1:30. But in reality, it's not that simple of a question. I picked this date on purpose. One, it's far enough in the past that people may not remember what happened on November 7th, 2010, that's several years ago. And 2, because this happens to be the day when the part of the world that recognizes daylight savings went from daylight savings back to standard time. And that happens at 2 a.m. So the hour from 1 a.m. to 2 a.m. occurred twice on November 7th. So in this case, it may be true that 1:15 a.m. is before 1:30 a.m. It may be that they're 15 minutes apart. It might be that they're an hour and 15 minutes apart. It's also possible, though, that the 1:30 a.m. event occurred before the 1:15 a.m. The 1:30 a.m. event occurred, and then we got to 2 o'clock. The clock rolled back to 1 o'clock. And then at 1:15, the event occurred, meaning that these events were 45 minutes apart. So the problem here is that if you're using a non-date time offset, a non-UTC data type, you can't create unique times when you're falling back from daylight savings to standard time. And likewise, those data types will leave a hole during the spring forward when you go from standard time to daylight savings. You may think, oh, that's not a problem. Well, it's not a problem unless you have an application where something is supposed to happen every 15 minutes. All of a sudden, during this spring forward time frame, it looks like it went a whole hour and 15 minutes without executing. It went from 1:45 to 3 a.m. So you need to recognize issues with daylight savings and times. Maybe in your application, you look at it, I really don't care. If we have a little bit of date time, there's a period of time where we can't distinguish dates or a date where there's a big gap, I really don't care. In which case, great, you're good to go. But you should at least think about it first. Okay, here are 2 other date and time events. Now, these are on different days, and they're on different times. And the question that I want you to answer here is how many hours were between these two? How far apart are these two date and time values in hours? I'll give you just a minute to think about it. Okay, the first thing you may have thought of, and probably rightfully so, is, well, when did we spring forward? When did we go to daylight savings time? But there's some other things you need to think about as well. Specifically, where did these events occur? Aha, I need an S right there. Where did these let's see if I can add it. Hello, mouse. Thank you. Where did these events, there we go. Where did these events occur? If they occurred in the same time zone, they could be 25 hours apart, right? If we didn't have any daylight savings changes, then the same time zone, the same place, they're 25 hours. But if they're in different time zones, maybe they're only 24 hours apart. One occurred both of them occurred at 3:15 p.m., but one was in a time zone that was further ahead or behind. Or if it happened in the opposite direction, it would be 26 hours apart. Or if they were more than just one time zone apart, it would be more or less than that. And again, as we saw in the previous slide, you also need to take into account whether or not it crossed daylight savings boundaries. So the difference between these two date and times is kind of ambiguous unless they happened in the same time zone and within the same daylight savings boundaries. So as you're storing date and time values, you also need to take into account the location of the event, where it occurred. All right, let's look at one more slide here. Here's my note. Non-daytime isolate data types cannot precisely compare times from different time zones or daylight savings periods. Now the date diff here is SQL Server's function for doing math between two date and time values. When you add and subtract them, how many hours are between these two? A date diff will tell you the number of hours, the number of seconds, the number of days that where boundaries are crossed between two periods. So that's the date diff function. Okay. Here is another date and time, November 10th, 2010, 2100 GMT. So here I've specified GMT time. I've also specified a time, and I picked a date here, November 10th, 2010. It's past November 7th, so you know that this is in standard time. So the question I want you to answer for this slide is, I want to display this date and time to the user. What do I show? So to answer that question, we have to say, well, what do you want to show? Well, it'd be easy enough for me to show 2100 GMT. Here you go. But often you'll want to convert this back into the time zone that the user understands. If they're not in the GMT time zone, they probably want to see it in their own time zone. So let's assume that you can figure out that they're in the mountain time zone. All right, so there's two options here. If November 10th is in standard time, then its standard time for mountain time zone is -7, so that would be 2 p.m. that we would show. However, if they're still in daylight savings, then that would be -6, which would be 3 p.m. Now I just told you, the reason I picked this date is because we're in standard time. Well, I knew that, and you knew that because we've been talking about here in the slide. But if I hadn't told you that, would you know whether it was in daylight savings or standard time? Chances are you wouldn't. You would need something to go look it up and say, okay, November 10th, is that standard time or daylight savings time? And then you could convert the time after that. But you would need to find a way to determine that. SQL Server doesn't have a way of telling you, this data is in or out of daylight savings time. So you need to find that somewhere outside. In this case, it's standard time, so the correct answer would be, 2 p.m. That is the date that we would show. Well, maybe. Let me add in another piece of information. What if the data for November 10th, 2010 was entered on July 10th? Now, July 10th, we would have been in daylight savings time, where we would have been at -6 hours GMT. So if we had the time we had tried to store was 3 p.m., we went ahead and added 6 hours because we were at -6 to make it GMT, and then we stored 11/10/2010, 2100, because that's 3 p.m. plus 6 hours is 9 p.m. 9 p.m. is 2100 hours, so that would be the 2100 GMT. Well, if we had stored it that way, 21 GMT, Then on November 10th, we're in daylight savings. If we had subtracted 7, we're using a different set of math to store it. We're adding 6 to store it, but when we're displaying it, we are subtracting 7. So we would get the wrong time, where what we had wanted to store was 3 p.m. What was displayed to us later was 2 p.m. because our math ended up being different, 7 versus 6. This is an interesting issue or an error that happens if you store your date based on the current time and not on what it is on the date that you're storing. I'm going to come back to this in just a second and give you a solution that one of our developers came up with that I thought was really clever. I'll do that in just a second. But I want to ask one other question first. That's, what if the user is traveling? So the user normally lives in the mountain time zone, but they're traveling in Hawaii. Now, let's assume that the correct time was 2 p.m. It's 2 p.m. at home. But where they're currently at in Hawaii, it's 10 a.m. Which do you show? Do you show the 2 p.m. or do you show the 10 a.m.? I don't think that, like some of the other questions, I don't think there's necessarily a pat answer that I can give you to this, but it's something that you should consider with your user base and what they might be doing. Let me give you an example. If what you're recording is an appointment or a meeting time, then what you would probably want to show is the current location time. They want to know, you know what, that meeting that you're supposed to attend is at 10 a.m. If you call into that meeting or connect up to that meeting or assume that that meeting is happening at 10 a.m. in Hawaii, you're exactly right. It's happening at 10 a.m. in Hawaii and 2 o'clock in the mountain time zone. That will allow you to coordinate. However, if you are recording an order time, it might make more sense to store or to display the 2 p.m. If you said, oh, your order was placed at 10 a.m., they're like, no, I didn't place that order at 10 a.m. I remember it was 2 o'clock when I placed that order. In that sense, the user's mindset is in their home time zone. They're thinking of the time where they were when it happened. They're thinking, yeah, I placed that order at 2 p.m., that's right. If you change the time and display it, oh, well, really, it was 10 a.m. in Hawaii when you placed that order at 2 p.m., then you're going to probably mess them up just a little bit. So that really depends a lot on your user base. You need to do some analysis to determine what you want to show. So these decisions, how you store the data and what you store, are really, for the most part, business decisions. They're not technical decisions. They're not database decisions. They're business decisions on how you want to show it. In fact, in some cases, you can get away with always showing user time rather than UTC or server time. What time was it where you are when this event occurred? What time was it where you were when this event occurred? Not what time was it at the server when it occurred, or what time was it where you are now when you did what it was when you were then. I hope that makes sense. All right, so our takeaway from this is storing data in GMT and UTC from a single location, for example, the server, is easy, but doesn't make the display easy. Now, I told you I'd come back and I would tell you what one of our developers had done for this problem here. And the problem is data entered on one date using math, and that time then is calculated later. What they did was they found a library that would allow them to determine on a particular date and time what the UTC or GMT value would be in from a particular location for that time. So they would pass in, they'd say, okay, mountain time zone, 3 p.m., February 2nd, 2016. And it would come through and say, okay, in the mountain time zone on that date and time, this is the UTC, this is the GMT time. Okay, great. And so they store that. That allows them to say, well, okay, the database it's stored as GMT on that date. All I need to do is convert it back to my date and my time from there. And that allowed them to not have to worry about this issue here, because they didn't store it. They didn't do the math. The library, instead of only adding the 6 hours, would say, okay, on this date and time, they're going to be in standard time. So a 3 p.m. in that time zone is going to be 22 hours instead of 21. So it would actually store the 2200 hours so that we got the 3 p.m. back out correctly when we moved into into standard time. I thought that was a pretty brilliant solution, and it solved a lot of problems that we had. Okay, so today we have talked about the data types that are stored in SQL Server in a database, or excuse me, the objects that are stored in SQL Server. We touched that briefly on that first slide, and then we talked about the numeric data types that SQL Server has, the datetime and datetime data types that SQL Server has available, and how to determine when you want to use each of these data types using the domain that they cover and the amount of space that they take up. All right, if you have any questions about the data types that we discussed today, feel free to contact me, and I'll do my very best to answer your questions. You can either drop by and see me at my desk, and we'll talk in person, or you're also welcome to either send me an email or send me a short note on Twitter at UVAChat. Thank you, and we'll see you in the next session.